Now, I just want to point out one other thing that you may or may not have caught as you were doing your activity, and that is the difference between what we call electronic and molecular geometries. Okay, the electronic geometry is telling me where the regions of high electron density are. For example, this molecule is ammonia. Okay, from the formula, you wouldn't necessarily know what the geometry is. You have to work out the Lewis structure. And when you work out the Lewis structure, you find that there's one non-bonding pair of electrons and then 3 bonding pairs of electrons. So there's a total of 4 regions of high electron density. So if you had your 4 balloons representing those 4 regions, it still looks like a tetrahedron. So the electronic geometry is tetrahedral. Okay, the electronic geometry, or the regions of electron domains, is tetrahedral. Okay, but the actual molecular geometry, what does the molecule look like? You just look at the positions of the atoms, and in this case it looks like a trigonal pyramid. All right, so the molecular geometry is different than the tetrahedral, the molecular geometry is different than the electronic geometry when you have a non-bonding region on the center atom. And this is called trigonal, this particular molecular geometry. So this would be the electronic geometry, and the molecular geometry would be trigonal pyramidal in this case. Okay, you see the same thing with water. Water, the formula for water, this is water, is H2O. You can't tell by looking at the formula what the three-dimensional geometry is going to be. You have to work out the Lewis structure, and in the Lewis structure you'd find that there's 4 regions of high electron density. 2 of those regions have bonding pairs of electrons, so the actual molecular geometry looks different than the electronic geometry. The electronic geometry here would also be tetrahedral. It's tetrahedral here and here, but the molecular geometry here would be bent or angular. It goes by either name. Okay, so what does the molecule actually look like? That's what the molecular geometry is telling us. And in this case, in methane, the case of methane, methane is CH4, and there are 4 regions of electron density, and there's 4 bonds. So in this case, the electronic and the molecular geometries are the same. They're both tetrahedral. And then we have the comparing methane to ammonia to water. They all have tetrahedral electronic geometry based on their Lewis structures and the non-bonding pairs of electrons that exist on these, but they have 3 different molecular geometries. Okay, and I want to show you one more. This picture might look kind of complicated, but just in case, I want you just to be aware that there are several different molecular geometries. We're only looking at, this angular also goes by bent. Okay, those words are used interchangeably. But we'll see linear, bent, trigonal planar, trigonal pyramidal. We won't see T-shaped and tetrahedral. These are all common shapes that can obey the octet rule. If you see T-shaped, this one has the electronic geometry of trigonal bipyramidal. There would be 2 non-bonding pairs of electrons there to force those atoms into that shape. So this would be an expanded valence situation. This one would have had a non-bonding pair here. This is an expanded valence. Square planar would have non-bonding on top and bottom. This is an octahedral geometry, electronic geometry, square planar molecular. Trigonal bipyramidal is the same electronic and molecular. This is an expanded valence with 5 regions of electron density. Square pyramidal, there would have been a non-bonding pair on the bottom. And then there's the octahedral that has 6, and then this is an extreme case, we won't even think about that. So I just want you guys to be aware that there's lots of different molecular geometries, and if you do go on in science, there's some real interesting molecules that have these geometries, but I'm not going to hold you to memorizing these names. I'm just holding you to memorizing the ones that I circled. Okay? And also I just want to throw these rules up there too. The rules for determining the molecular geometry are slightly different than the electronic geometry. In both cases, you need to determine the Lewis structure first. If you get the Lewis structure wrong, you get the whole thing wrong. In both cases, you need to determine the number of regions of electron density, which will give you the electronic geometry, and that's in other words, the domains. Once you figure that out, you determine the number of non-bonding pairs of electrons on the central atom. If there's no non-bonding, then the electronic geometry is the same as the molecular geometry. If there's one or more non-bonding pairs of electrons, then you determine the molecular geometry based on the shape of the atoms. And that's what I gave you back here. You could have angular, and the electronics trigonal planar or tetrahedral, or you can have trigonal pyramidal, and it's got one non-bonding pair, and it was tetrahedral. Okay? And so then also you want to be able to predict the bond angles allowing for distortion. And that is if you have non-bonding pairs of electrons, and you should have seen this in your POGIL activity, non-bonding pairs of electrons on the central atom reside closer to the nucleus, or closer to the atom, closer to the nucleus. So they repel the bonds more. Okay? And so what is meant by that is if you look back at this picture right here, the pure tetrahedral bond angle is 109.5, and even though this has electronic geometry, the bond angle here is 107 because the non-bonding pairs of electrons that are on this central atom reside closer to the central atom, so they're going to repel down more on these three bonds and push them a little tighter. So they're about 107. And then for water, you have two non-bonding pairs of electrons, so you have more push down on these bonding pairs because the non-bonding pairs reside closer to the central atom because there's no other atom, to pull them further away. So they push down more, and that's even a smaller bond angle of 104.5 in that bent structure. That's what that last predict bond angles allowing for distortion means.